Every time we write code, we're really just communicating an idea. But there are so many layers of abstraction between our logic and the silicon chip that actually runs it. If you truly want to understand computing, you have to peel those layers back, one by one, all the way down to the metal, to the place where software and hardware finally meet.
So, have you ever really stopped to think about that? What is actually happening when you hit run on a script? How does a processor, which is just a piece of silicon that only gets on and off, how does it execute your complex ideas? Well, today we're going to answer that. We're going to explore the very bedrock of all software.
All right, let's jump right in with an analogy I love. Think about writing in a high-level language, like Python. It's kind of like being an architect who hands over a blueprint that just says, build a building. The high-level goal is crystal clear. But assembly language, well, that's the super specific step-by-step instruction sheet for the builder who's actually on the ground. It's not build a building. No, it's take one brick, apply the mortar, place that brick right here, and you repeat that thousands and thousands of times. It is all about precision, not abstraction. And that, right there, is the perfect lead-in to what assembly language truly is. It's often called the CPU's native tongue. It's this absolutely critical bridge between our symbolic, human-readable ideas and the raw binary, the ones and zeros, that the processor actually understands. Okay, so here's the really crucial thing to get your head around. Assembly isn't just one single universal language. It's actually a whole family of languages. See, each processor architecture, like the x86 in your laptop or the ARM chip in your phone, has its own unique set of machine code instructions. And because of that, it has its own very specific assembly language. There's a one-to-one relationship between the assembly command and the hardware's command.
Yeah, and this is where it gets really cool because you can actually see that connection. On the left, you got raw machine code, just a string of ones and zeros that, let's be honest, is completely meaningless to most of us. But on the right, you have the assembly equivalent, move AL value. That word move is what we call a mnemonic. It's just a short, memorable abbreviation for the move instruction. The whole job of the assembler program is to translate that human-friendly word directly into that specific binary string. All right, so if our CPU is the builder, what's on its tool belt? What does the worksite actually look like? Let's explore the tools it uses to follow our very specific instructions.
Well, the most fundamental tools, by far, are the registers. You can think of them as the processor's own personal scratchpad. See, going out to the main computer memory, the RAM, is actually pretty slow from the CPU's perspective. So instead, it uses these tiny, incredibly fast storage spots right there on the chip to hold whatever data it's actively working on at that very moment.
And that toolbox analogy is just perfect. If the main memory, or RAM, is the giant supply warehouse across town, the registers are the worker's toolbox strapped right to their hip. It can't hold very much, but whatever is in there is immediately accessible. And that right there is why registers are so fundamental to how fast a processor can run.
So if you're looking at x86 code, for instance, you're going to see these names pop up all the time. The EAX register, for example, is often called the accumulator. It's kind of the default spot for storing the results of math operations. Then you have ECX, the counter register, which is very frequently used to keep track of how many times a loop needs to run. Just understanding their basic roles is one of the first keys to reading assembly. And these are the actual commands the builder follows. And you'll notice they are ridiculously simple. MOV just copies data from one place to another. Add adds, sub subtracts. And JMP, or jump, is like telling the worker, hey, stop what you're doing and go to a completely different part of the blueprint. Every complex program you have ever used, no matter how sophisticated, is ultimately broken down into long sequences of these incredibly primitive actions.
Okay, but a program isn't just a random jumble of these commands, right? Just like any good blueprint, it has to be organized. It has very specific sections for the materials and for the work plan itself. Exactly. And this organization is so important. Think of it this way. You have the supply yard. That's your data section. It's where you keep all your raw materials, any data, constants, or messages you're going to need. And then you have the actual work site. That's the text section. That is where you lay out the step-by-step instructions that tell the processor what to do with those materials. And when you see it in code, it makes perfect sense. Just like the slide says, the .data section is for the materials, like our Hello World message. The .text section is for the actual instructions. This fundamental separation of what you're working with from what you're doing
is a core principle that brings order to the low-level world.
Okay, so this begs the question, right? If this stuff is so granular and, let's be honest, kind of tedious, why on earth are we even talking about it today? Why hasn't it just gone away? Well, because it offers a level of power that comes with a massive trade-off in simplicity.
This table really breaks down those trade-offs beautifully. With assembly, you get the absolute maximum performance possible and total direct control over the hardware. But that power comes at a steep price. Your code isn't portable. Code for an Intel chip is not going to run on an ARM chip. And the complexity is just immense. High-level languages like Python give you portability and let you develop way faster, but you have to sacrifice that fine-grained control and that raw speed. Right, so to be clear, you are not going to build your next website with assembly. That is not what it's for. This is for the stuff where performance and direct hardware control are completely non-negotiable. When your computer first boots up, that's assembly. The firmware in your car or in a medical device, the device drivers for your hardware, the absolute most performance-critical parts of game engines or cryptography. These are the places where assembly isn't just relevant, it's indispensable. So let's zoom back out for a moment, because really understanding assembly, it changes how you see everything else in computing. You start to see this unseen foundation, the solid bedrock that all modern software is actually built on. And this quote, I think this really gets to the heart of it. When a computer powers on, before any operating system loads, before a single line of high-level code is run, it is assembly that breathes the first spark of life into the machine. It was, and it still is, the essential bridge from our intent to the machine's action. And that's the bottom line. Think back to our construction project. That gorgeous, high-tech skyscraper the architect designed, at the end of the day, it's still built brick by individual brick. Every single line of Python or Java or C++ that you write is eventually compiled or interpreted down through all those layers until it becomes these simple assembly instructions that the hardware can finally execute. In the end, it's all assembly. So, we want to leave you with this one thought. Now that you know what lies beneath it all, the registers, the simple instructions, that direct conversation with the hardware, how does that change the way you look at the high-level code you write every day? Because once you understand the foundation, the entire structure starts to look a whole lot different.